Hi, everybody. Welcome to part one of a five-part webinar series focused on everything you need to know about thermal imaging drones in the solar industry. My name is Brett Conda, and I'm joined by my co-host, Austin Coffin, Head of Sales from Raptor Maps. Welcome, Austin.
Thank you for having me, Brett. I'm excited to be here and discuss this super important topic with you all today.
Fantastic. So what we're going to be discussing today is the following. What is manual electrical testing for PV fields? How is manual electrical testing performed? What does manual electrical testing find? The basics of aerial thermography, thermography considerations for solar inspections, and then best practices and conclusions. So Austin, tell us what exactly is manual electrical testing?
Manual electric testing, which is actually commonly referred to as IV curve tracing, is an electrical test that is used to inspect and identify the performance of a solar array. The test is always performed by highly trained technicians, and these technicians are spending a lot of time and effort and have to have a lot of skill to properly perform this type of test. This type of inspection has been performed in the solar industry for several years, and today it is one of the main ways that companies own, manage, and maintain solar farms are approaching finding issues that impact the performance of their assets.
Perfect. Thanks, Austin. So now that we have a better understanding of what manual electrical testing is, how exactly is that performed in the field by these highly skilled technicians?
So this test or inspection is performed by using special handheld electrical testing kits that require quite a bit of training and ideal environmental conditions to get successful test results. The test is also performed within a specific period of time. What this means is that the solar farm is operating at a certain radiance, or essentially is energized at a certain level of watt per square meter for the test to be valid. The test is also performed by manually walking up to each string of PV modules that are to be tested. The string is unplugged from the array, plugged into the testing device, and then the technician is measuring the output or curve from that string and comparing these results or output to the expected results. All of these results that they're getting from the readings have to be manually interpreted also by the technician who's taking the reading to understand essentially if things are operating correctly or not.
So obviously it takes a long time to walk up and down these fields to conduct manual electrical testing. But once that technician has gotten to his string, what exactly are they looking for and what does manual electrical testing find?
Yeah, I would say a long time is an understatement here. It can take several hours and if not days for a small site, let alone a massive site like we see today in the space. The technicians are looking for 5 different types of impairments. An impairment obviously is something that is affecting production of those modules and strings, but high level, there are series, shunt, and or mismatch losses. There are also reduced current and reduced voltage impairments. All of these losses or impairments are due to issues that could be caused by soiling, issues related to shading, resistance built up in the modules and strings, mismatch of modules, or several other different types of issues that are common today in these sites.
Thanks, Austin. So now we know what's being done in the solar industry currently, and this is where thermal imaging drones comes in. At FLIR, we focus on the infrared band of the electromagnetic spectrum, and that allows us to do the following things: see in total darkness, see through obscurance, measure temperature, enhance long-range imaging, and accurately detecting people and animals. For the purpose of this webinar, we're going to focus on measuring temperature and being able to easily identify problems with solar panels. When collecting aerial thermal data, there's a few things that you need to consider when you are collecting this data to ensure that it is accurate. Here are some of the basics of aerial thermography. Radiometry is a set of techniques for measuring electromagnetic radiation, including visible light. So if you're doing a quantitative analysis of a solar field, this is going to be something that you need to focus on to make sure that you're collecting that right temperature. Emissivity is the ratio of energy emitted by an object compared to the energy emitted by a black body at the same temperature. Emissivity settings can be found in your ground control station or your app based on what camera you're flying. It is crucial to have proper emissivity settings prior to flight. The acronym FORD stands for focus, range, and distance to target. These are 3 aspects that cannot be changed in a post-processing software, so you have to make sure that you are in focus, in range, and your distance to the target is accurate based on your camera resolution. These are crucial when it comes down to collecting accurate data, and again, these are 3 things that cannot be changed in post-processing. A couple other basics for aerial thermography is isotherms. Isotherms is a measurement tool that highlights areas of equal apparent temperature. This would allow anomalies to stand out when you're collecting your data and makes things much easier to see. Reflective apparent temperature is the apparent temperature of objects whose radiant energy is reflected off the target into the camera. This is important because solar panels tend to be highly reflective and therefore have low emissivity, so you have to ensure your settings are correct to get proper data. A few other considerations. Like I said, you have to make sure you set the proper emissivity settings prior to flight. As Austin will touch on in just a minute, it is crucial to use a dual payload. You need to have thermal imagery as well as RGB visible imagery to make sure that you're not having any false positives when you're collecting your aerial thermal data. You have to consider the environmental factors. Humidity, wind, air temperature, and time of day are all considerations that you need to look at prior to flight. You need to optimize your hardware for best results. That means a high frame rate and a high resolution on your camera, as well as enough flight time to be able to collect data on your entire field. You have to understand reflections and reflective apparent temperature, which I just mentioned, because again, solar fields are highly reflective. If you are doing quantitative analysis, you have to ensure that the appropriate target temperature range is set in your camera prior to flight. And again, in future videos, we are going to be deep diving some of these factors to make sure our listeners have an exact idea and an exact way to execute in the field to ensure proper and accurate data. So Austin, now that we've talked about manual electrical testing and the basics of aerial thermography, run us through a conclusion and some best practices for our viewers.
Can't stress enough that it's extremely important for everyone to have a basic understanding of thermography, just to correctly be able to perform an aerial inspection of a solar plant. By far the worst thing you could do is spend an entire day or several days performing an inspection with your drone on site, several hours from where you live, in performing this in the wrong conditions, with the wrong equipment, on the wrong settings, and ultimately creating a lot of data that is not usable. Also, aerial thermography as a whole is an extremely powerful tool that can be used to quickly inspect large areas. When you're out there and you're inspecting and capturing thermal data on several hundred acres of PV modules, doing it the right way, you can scan several hundred acres within a single day. This data also enables you to assess the condition of each PV module at the cell level later on when you're doing post-processing with a tool like Raptor Maps, and then ultimately finding the areas within that site that are impacting performance and require a closer look, which is then, manual electric testing is also another powerful tool that can be used to closely examine those specific areas of the solar farm that are known to contain anomalies or issues. When you combine the data and the results from aerial thermography with manual electric testing, you really have an opportunity to make better and, I would say, more data-driven management decisions. So anyone in management or a decision maker has a better ability to understand where to deploy their field technicians in a more efficient way. Also, having data before a site visit will allow the technicians to be better prepared for the work that needs to be performed. And also, as you said earlier, I cannot stress enough how important it is to collect both radiometric thermal and high definition visual imagery. These two data sets allow you to correctly identify a thermal anomaly. What that means is that the high resolution RGB visible imagery will allow you to confirm if that thermal anomaly that you are seeing in the radiometric thermal image, or the RJPEG, if that is actually an electrical issue impacting performance, or if it's a false positive caused by soiling or shadowing of the module.
Austin, thanks for your time and insights. Much appreciated, and I know our viewers are going to have a better idea of how to properly inspect solar fields with thermal imaging drones. If anybody has any questions, please feel free to contact me. This is my contact information here, and stay tuned for future episodes of this webinar series on thermal imaging drones for the solar industry.